EET 114, Chapter 17, Series Parallel AC Networks, Problem 11. For this network shown down here, find the total impedance Z sub T. So the first thing you notice about this circuit is that the voltage is given to you as a sinusoid, okay? And the other thing that you notice is that the elements are given to you with their base values. The capacitor has capacitance, inductor has inductance. So first thing you have to do is you have to convert each element to complex number. You have to convert the source voltage again to a phasor. So when E equals Vm sine of omega t plus theta, then the phasor E equals V sub m divided by the square root of 2 angle of theta. And R equals R plus R angle of 0. L equals J omega L with omega or omega L equal angle of 90. And C equals, it's really hard to see, minus J omega C, which is 1 divided by omega C angle of negative 90. So E in this case for this problem would be square root of 2 times 50 divided by the square root of 2 angle of 0, or just 50 angle of 0. Okay, so that's step 1. Step 2 is we're going to convert all elements to impedances using these equations here. So we see that our omega, and again, a lot of people get mixed up with this, and I keep saying it over and over. Omega is whatever's between the sine and the t. So you could put all kinds of stuff in here. 2 pi times 1,000 divided by 1,500 times 3, whatever. This thing in here is the omega. That's all it is. So in this case, the omega is 2 pi times 1,000 radians per second. Now F is omega divided by 2 pi, so F is just going to be 1,000 hertz. We're going to need that soon. So what I did, the book completely botched this solution, so I had to write it down and do it by hand. So I'm going to break down each impedance in rectangular and polar form. So I called this ZR1. That's going to be 300 in rectangular form. In polar form, it's 300 angle of 0. ZL1 is going to be J omega L or omega L angle of 90. So that's going to be J times 2 pi 1,000 times 0.1, because that's the inductance given. That ends up equaling J 628.3 ohms, which is also equal to 628.3 ohms angle 90. Z sub t is minus J divided by omega C, which is 1 over omega C angle negative 90. So that's equal to negative J divided by 2 pi times 1,000 times 1 microfarad, which ends up equaling minus J 159.2 ohms, which is equal to 159.2 ohms angle negative 90. And lastly, L2, ZL2 is equal to J omega L equal to omega L angle 90, which ends up equaling, it's just double what this thing is, because this is 0.2 and this is 0.1. So that's J of 1256.6 ohms equals 1256.6 ohms angle 90. So then you have to find the total impedance and source current. Total impedance, I like to start from the right side. So you have C in parallel with L2, so Z sub P in parallel with ZL2, and then you add the ZR1 and the ZL1 to that because they're in series with that. So when you do this calculation, I wrote it down, like I'm not going to describe all of that, but You have to multiply these two numbers and then divide the sum of the two numbers. That ends up giving you, when you do that, you get minus J 182.3 plus 300 plus J 628.3, and then the total in rectangular form is 300 ohms plus J 446 ohms. And again, I probably rounded a little bit there. Then that ends up equaling in polar form 537.5 ohms, angle of 56.07 ohms. You'll see later on I start just rounding that to 56 degrees. What did I say, ohms? I meant degrees. 537.5 ohms, angle of 56.07 degrees. And then the source current is E divided by the total impedance. So E we figured out over here to be 50 angle of 0. So 50 angle of 0 divided by 537.5 angle of 56 degrees is 0.093 amps, angle of minus 56.07 degrees. Part C is asking you for find the currents I1 and I2 in phasor form. So I1 is the current going through the capacitor, I2 is the current going through L2, the inductor. So you have to use the current divider to find each current. So for I1, you take the source current, which is coming in through this leg, and it's still I sub S coming in here, and it gets divided off into I1 and I2. So again, I1 equals I sub S times ZL2, because that's on the other leg that you're looking for the current over here, but you have to put in the impedance in the current divider equation of this impedance of the opposite leg in the numerator. And then you sum the two impedances in the denominator. When you do all that math, you come up with 0.106 amps, angle negative 56 degrees. And then I2, there's two ways that you can solve for that at this point. You can use the current divider again, this in a similar way to find this current. So you put this impedance in the numerator and then put the sum of the two impedances in the denominator. Do that math and you come up with this. Or you could just take I2 equals I sub S minus I1. Okay, since I sub S is coming in, I1's coming out, so I2 is the remainder. And you get basically the same number here. Okay, you're going to very close number. Part D says find the voltages V1 and VAB in phasor form. Okay, so V1 they called the voltage across L2. So let's look at that one first. We already found out what I2 is. So V1 is going to be the current going through that inductor times the impedance of the inductor. So you just take those values that you already know, multiply them out, and you get that answer. VAB is a little bit tougher to see. So VAB is the voltage between this point and this point, okay? So one way to do it is you know what E is. All you have to look is the voltage drop across R1 and you got VAB. That's a simple way. So I took VAB equals E minus VR1. So E is 50 angle 0. VR1 is I sub S times R1. So I multiplied this and subtracted it from the 50 angle of 0 and got 41.45 angle of 33.91. The other way to do it is do a voltage divider. Okay, so the way that you have to do this voltage divider is you have to take this entire impedance right here, these two guys in parallel, and then series with this guy. And then look at that as one single impedance, which we already did figure out before. I think I called it ZT prime up above here. All right. ZT prime is ZC in parallel with L2 plus L1 which ends up equaling this J446 portion. All right. It just happened to work out that way. You'd have to do the math to confirm it, but you could see from up here, Z sub t plus L2 was um, that J negative J 182.3, and you add that to ZL1, the positive J 628.3, and that ends up being J 446. So when you do that math and you take E times Z sub t prime divided by ZR1 times plus Z sub t prime, that ends up equaling Z sub t. You already know what Z sub t is. So you multiply this out and divide, and you get 41.49 angle of 34 degrees, which is very similar to the answer over here. And then the last part, well, the next to last, E, find the average power delivered to the network. So again, we use this equation, power equals EI cosine of theta t. E ends equaling 50. I we already figured out to be 0.93, and cosine is theta v minus theta I absolute value. So this ends up being 4.65. The cosine is theta v was 0, and theta I is a negative 56. So that's cosine of 56, which is 2.6 watts. And then part F is find the power factor, which is just this part of this equation, okay? So it's cosine of 56, which is 0.559. And in this case, theta v is greater than theta I, 0 is greater than negative 56. So we have Eli because E comes before I. So theta v is greater than I. Comes before I. That means it's inductive, and that means the current lags the voltage. And that also means that the phase angle, the ZT phase angle, is positive. If you go over here and look, when we originally found ZT, where was that? Right here. This phase angle is positive, which means right away you should know it's inductive, and you should know that the current lags the voltage. I also did this problem. I'm not going to go over it again, but I did it all in Excel over here, just for your edification, and it confirms all the hand calculations that I did. I just plugged and chugged numbers here. I converted sources from sinusoid to phasor. Then the impedances are not given, so convert elements to impedances. And I converted to both forms. I converted this to both forms. I converted everything to both forms. Then I combined impedance from right to left to get total impedance. Then I found the source current, and I used the current divider on each one to find each current. Then I used Ohm's law to find the voltage across L2. And I used, again, KVL to find this voltage, AB. And then the average power delivered in the circuit. This is the total power, 4.65. The average power is 2.60. And the power factor was 0.558. Current lags the voltage. It's inductive.